Okay, so part one of our two-part series for today. We're again reviewing some of the important things we learned about stars. All right, so we talked about this term luminosity, right? And we have brightness, I think there's two S's, and intensity. So a brightness and intensity, these are kind of the same. If you divide, the luminosity is a power, right? So in units of watts, so that's energy per second. And then if you divide it by area, you get brightness. And that's how brightness, because that's also intensity, right? How bright something is just another way of saying how intense it is. And then we have distance. Yeah? And so what this allows us to do is luminosity, we can't really get to stars to see how powerful they are, but we can measure the intensity of the brightness, and we can measure how far away they are. And we'll get to the slide. This gives us, and this little, remember, wherever you see one of these weird squiggles that it couldn't transcribe correctly, that's the Greek letter pi. Okay? So the right way to write this is equal to luminosity over 4 pi d squared, where d is distance and L is luminosity. Now, I like this version better, right, where this should be 4 pi d squared times brightness. Usually you'd write an I for intensity, and we're going to call this L equals. Why do I like this better? Because this shows us stuff we can measure on one side of the equation in terms of stuff we predict on the other side. All right? Physics, elegant physics, is usually expressed in this way, which is stuff you can measure readily in the lab on one side of your math, and then stuff you can predict or can't measure readily in the lab on the other, that you would predict based on your measurements in the lab. So that's just good convention in physics. So we saw that, and the next thing we talked about, again, there's more details on measuring distance and things like that in the last week's lab. We talked about our the ranges of stars we can see. We talked about a lot of the stuff. The place where I'm going to stop, though, is in our summary slide. For our review, we talked about binaries, two-star systems, and how we measure them. It gets us all the way. I don't want to talk about the Hertzsprung-Russell diagram yet. Man, here we go. This was the slide I was looking for. Geez, took a while to get there. So as you can see, the ranges of luminosity, we had then covered temperature and mass, and we found that the luminosity range is quite big. And you'll notice everything is in terms of our sun, right? So that's a fraction of our own star. And we can see here, interestingly, that the least luminosity is about 1/10,000th the luminosity of our sun, and the most luminous is about 1,000,000 times as luminous as our sun. Temperature goes from 3,000 Kelvin, that's about half as hot as our star, to about 50,000 Kelvin. Again, the surface of the sun is about 6,000 Kelvin. And the mass goes from 0.08 solar masses to 100 solar masses. Now these represent stars' stellar property review on the main sequence. Okay? So you'll notice that luminosities, temperatures, and mass all track with each other as long as you're on the main sequence. And if you remember, a star is on the main sequence if it is converting its core hydrogen into helium via nuclear fusion. Okay, that's the important distinction That's the important criteria of being in the main sequence. Now you can be off the main sequence, but then other things are happening, higher fusions are happening. The stars off the main sequence are unstable. Okay, so let's look at our Hertzsprung-Russell diagram to help us catalog stars. I just want to get back to this. Man, it is hard to find the good pictures. So you'll notice that our main sequence line for our HR diagram is this straight line. Okay? So when we did that summary slide, everything there applies, and you'll notice that you have small mass, low temperature, low luminosity stars on this end of the line, and you'll have high temperature, high luminosity, high mass stars on this part of the line. But if you look at these giants and supergiants, these are off the main sequence. Your white dwarfs are off the main sequence. So we're actually going to spend a little bit of the next chapter and the chapter after looking at star formation, sort of how stars are born, which we've already seen a lot of, but we'll look at some pictures of evidence of star birth, sort of fill in some gaps. And we're also going to look at, in the chapter after, we're going to start to look at how stars die. All right, and that's where we get into these supergiants, giants, and then white dwarf phases. All right, so so again, this graph is a little strange, right? The luminosity is pretty obvious because it goes up, but its scale is not very traditional. Its scale is exponential. So what you can see there is that each one is 10 times, each tick is 10 times more than the one previous. So each one is only 10% of the previous one, right? But it moves in the positive direction you'd be used to from a traditional math class. Now, the axis here is fairly linear, right? So that looks like what you'd see in a normal math class, but you'll notice that the positive direction is towards the left, not the right, okay? So you have to keep that context in mind and not just make assumptions about your coordinates. All right, so and that's how to read this graph or these diagrams. So we talked about different types of stars, and we started to allude to what happened after we left the main sequence. So where we ended, we talked about lifetime. That's one thing to see. The heavier the star, the lower the lifetime. And we saw that the star's lifetime range could range anywhere from 1 million years for the most massive stars to 1 trillion years for the very least massive stars, right? And so we saw this main sequence summary star. And you'll notice our sun, this is a little misleading because while our sun is very small compared to, say, Spica and Sirius, you will notice you're going to see soon that the vast majority of stars are around Proxima Centauri's size. They are not really the size of our sun. So I like, and we'll see it, but our sun is solidly, I guess you would describe it, above average. So you know, I'll get into more detail about that when we get there in the next chapter. But it's a little misleading. But if we go off the, and we saw of course all the features of a star cluster, but when we get off the main sequence, right, interesting things will happen at the cores, and that will occur when the hydrogen is all used up in the core, and you have, and it becomes helium. So what happens there is the helium core is inert and begins to collapse. As it begins to collapse, it begins to heat up. And then interesting things can happen because you have no fusion going on, but that doesn't mean it's not hot enough for what we'll call shell fusion or fusion in other parts of the star to start happening, which is why they can get so much bigger. Most stars end up, after they die, will end up small and white after fusion and become white dwarfs, although some larger stars will become neutron stars, and the very largest stars become black holes when they die. So we're getting close to talking about black holes, which is usually, it's usually everyone's favorite part of the course, cosmology and black holes. So Giants and supergiants are far larger than main sequence stars. All right, you can see we have our giant stars here. We have Betelgeuse, which is a supergiant. We have Aldebaran, which is a giant star. And you'll notice this little dot here. That's the sun. Okay, so you have to zoom in 100 times to get the sun, and then you can see the Earth for comparison. So the Earth isn't even a pixel. So the sun is only a few pixels here. You have to multiply it by 100 times to get something this big. So when you're off the main sequence, your size can be very large. If you look here, a giant star, and you'll recognize these from our video last week, some of our characters. So you'll notice that the temperature is lower than our, but the sun is hundreds of thousands of times larger than the Earth. Yes, the sun is about 100 times, 100 Earths from end to end, from in the diameter. All right, so you can fit about 200 Earths across, but it's about 100 Earth radii in radius. You'll notice the temperature of the sun, though, is about 5,800 Kelvin. All right, so notice that Aldebaran here is 4,500 Kelvin. It's cooler than the sun, but its luminosity is greater. All right, so in that sense, we have 44. We get it's more luminous but cooler, which must mean that it's bigger. All right, so using those two things, which we can measure, we can figure out the temperature from the black body radiation curve, and we can figure out the luminosity from our brightness distance calculation. We get the size of 44 solar radii. All right, now that's not perfect. There's going to be some error bars, plus or minus a few, but you'll notice that Betelgeuse, which is a supergiant, it's even cooler, right? Its temperature is 3,800 Kelvin, but its luminosity is huge. It's 120,000 times as luminous as the sun, so it must be even bigger, and it's estimated to have a radius of 950 solar radii. Now, I want to remind you to give you in perspective about these energies, because it's easy to say, oh, 120,000 times as luminous as the sun, like it seems like no big deal. But keep in mind that the sun outputs enough energy every second, in 1 second, so one, then another. It outputs enough energy in 1 second to power 2020 humanity for nearly 1 million years. All right? And by nearly a million, I mean like 999,950 or something there, because all the power consumption charts are from 2015. 2015 wasn't that long ago. But yeah, so about roughly a million years of current human output, like everything, every country, every device you use, the sun puts out more energy in 1 second than doing that for a million years. So, fun times, huh? So when you look at some of these energy outputs, they're really, really staggering. Okay, so now we want to go back we'll warm up with some more questions on the Hertzsprung-Russell diagram. So which star is most like our sun? All right, if we look here, A, B, C, or D. Now think about our own star. When you ask yourself, is our star a giant or a supergiant? No. Is our sun a white dwarf? No. And how do we get those answers? We know our sun is still burning or converting hydrogen into helium. So that means our sun is going to be on the main sequence. And you can find the sun right here. All right? So the sun, so in order to be like our star, the answer would have to be on the main sequence. And the only one I see on the main sequence is D. Right? So that should be good. It's always good when things match up with our expectations. So now, which of these stars will have changed the least in 10 billion years from now? Let's see if we can get that one. So A will have cooled. I don't know if we're calling A a star though, which is a good question. So yeah, I mean A certainly won't have changed much in 10 billion years, but debatable whether we should be calling A a star. That's where I get confused. No, B, once we get up here, B very much is at the end of its life. So stars don't stay at the end of their lives for billions and billions of years. A, as a white dwarf, it's sort of like, the best way to ask this question, I think, with a human equivalent is if you look at people and you look at a corpse, right, and you ask which one of these will change the least in 1,000 years, well, the corpse will change the least, right, because all of the other ones will have died from then. So as we look at this today, A will change the least because it's no longer going under any transitions. My only issue is whether it's appropriate to call it a star, because it's a husk and it behaves differently. I guess that's one of those things that's left over from an earlier convention time. It's not really appropriate to call, because we call neutron stars stars, but we recognize them as non-stellar. They're stellar corpses. That's where I'm trying to be specific. Okay. So now we want to look at star clusters. All right. So we'll look at the. So no, see, this is where things get confusing in astronomy. That's a great question, Katya. Pluto is a dwarf planet, and a white dwarf is has a very high temperature, so it's associated with stars, and we can actually see white dwarfs form, and we'll talk about that in the next chapter. So the white dwarfs have masses on the scale of stars, but their radii is very small. It's like a planetary size. So imagine an object that was as massive as the sun, but the size of Earth, and that's a white dwarf, and that's why it's called a dwarf. Yeah. So whereas Pluto is a dwarf planet. So Pluto is small on the planetary scale, and white dwarfs have small size on the stellar scale. So we want to keep that in mind. And I actually want to draw that again. So, because sometimes these words get overloaded, and this is a good point. So remember, with our scales, we started with planetary, right? That was your planets, moons, asteroids, comets, dwarf planets, stuff like that. And then you have stellar, which is where we are now. And then we have galactic, which we'll get to soon. And then we have cosmic after galactic, but I ran out of room. All right. So we're right in the middle of this one. But this one is these two sort of take up more time because we have a lot more information here than we do with galactic and cosmic. Looking at individual stars as old as humanity itself, understanding different stars is only about 400 years old, and understanding different galaxies exist is a rapidly developing field now. And it was only determined that we weren't the only galaxy in the universe conclusively in 1920. So that's 100 years. And so I mean, when I was small, I certainly, my grandparents were born in the 20s and things like that. So of course, the cosmic scale is the galactic is a fairly rapidly developing field today, and the cosmic field, there's still lots of gaps, and it's a very rapidly developing field. So let's pull back and let's continue talking about star clusters, because we do get information by looking at the types of star clusters. No, people have never been to Mars. The only object besides the Earth that people have landed on is the moon. That's it. Everything else has been robotic. Or probes. Never inside. No, the deepest hole we've dug on Mars is about, I think it's 8 inches deep. I just saw something about it on Reddit. It was actually, I mean, it's funny because on the one hand, it's just a hole that was dug by a rover, but I thought it was really cool. It was a Martian hole. And it was interesting how the color layer changed so rapidly. The red is just like a tinted surface layer. But yeah, no, like caverns and caves in Mars, We've never, not to the best of my knowledge, we've never been inside anything. It'd be news to me. I mean, if you can find an article, I'd love to read it because I would find that endlessly fascinating. But I don't think we've been inside Mars. It's probably theoretically possible we could go inside, but you'd have to find an entrance and get in. So, all right. So we have two types of clusters. We have an open cluster, which is a few thousand loosely bound stars. And I want you to look at the colors here. You'll notice a lot of our stars are sort of blue or white. So these we find throughout the disk, and there will be a lot of young stars in these clusters. And again, remember, you can tell the age of, well, not remember, you can tell the age of a star cluster by the types of stars, right? If you have a lot of high mass stars, the cluster's not very old because high mass stars don't live very long, right? And we also have these globular clusters. You'll notice there aren't many blue stars in here. These can have millions of stars in a dense ball bound together, but you'll notice that these are mostly older stars. So you find these more towards the center of the galaxy, okay, or in the bulge of the galaxy. These individual clusters, but they can be found in different spots throughout. So you'll notice that the more stars you see on the high mass section, remember they can only live for about 1 million, 10 million to 100 million years, and then they'll all go away, and you'll only be left with the stars that live for billions of years, which are yellow and reddish type stars. Okay, there's actually a really nice. So if you look here, you'll notice you have blue, white, yellow, and red stars. All right. Now, if you, I mean, I wish we could do it, but I can't get these to work. But if you set the timer going, you play the simulation, you'll very quickly see that all the blue stars die very rapidly. And then very sort of less quickly, the white ones all disappear. And then slowly but surely, you're left with all the yellow ones go out, and you have at about 10 billion to 100 billion years, just these faint orange ones. The rest of the other stuff is all gone. And again, that happens because the more massive you are, the less your lifetime is. So we actually can look at the age, gauge the age of stellar clusters by just looking at the composition of how many high mass stars are in them. Okay? And so Pleiades, which I guess is a star cluster we can look at, now has no stars with a life expectancy less than 100 million years. So on the main, so we can see some stars off the main sequence, but on the main sequence, it's 100 million years or older. So it can't be much older than 100 million years. All right, and all the young mass stars have died, or are entering the main sequence, or exiting the main sequence rather. Okay. Let's see if I have any good pictures left of this chapter. Nope. Nope. Okay. Yes, much longer than Betelgeuse. In fact, Betelgeuse is speculated to go supernova anytime between now and 500, like today, and 500,000 years from now. Or maybe I think it's the next 100,000 years. We have a lot of error bars on this stuff. They might be bigger than you'd hope. But Betelgeuse was actually making the news recently because it was dimming and doing things that had never been observed before, and astronomers were speculating whether Betelgeuse was indeed beginning its final collapse and could go supernova within the next year or two, which would be pretty exciting because if Betelgeuse went supernova, and we'll understand what that term means, if almost certainly today, but if not today, then definitely next week. And we'll be able to, we would actually be able to see Betelgeuse. It would be very bright. As when it exploded, it would be incredibly bright for a very, very short time. But afterwards, for about 2 or 3 months, it would almost be as bright as the full moon. So that would be pretty spectacular. And it would be visible in the day, which would also be pretty spectacular as well. So, but yeah, Betelgeuse is not long for this world. It's sort of on its last gasp. If stars were people would be coming to say goodbye to it. It would be, it would be in hospice. Our star will be kicking along for another 5 billion years. So, just doing its thing, hanging out. And then after 5 billion years, I think it'll take another couple million years to do its death cycle. And then it'll be a white dwarf for a very long time. So I think that takes us out of that part of stars, and will take us to our next section on stars. So let's get there. All right. Okay. So now we're going to look at star lifetimes, all right? And we're going to go over star birth, but we're going to discuss and expand on it a little bit, but a lot of it is really just rehash from our chapter on the birth of the solar system, because when we talked about how the solar system was formed, a lot of that was the formation of our star. And a lot of that information that we got is I'm saying it's sort of cheating, because we use information from really what should be now in the course to draw conclusions about how our own sun was born. So we're going to go quick through some stuff, and we're also going to slow down on some stuff. But what we really want to do is sort of look and see the pictures that indicate to us stars are forming, and become familiar with the picture of star formation. All right. There's a lot of facts to it. Those are the facts that sort of connect the picture. But we'll go through and we'll see what we look for. So now we already sort of know how stars form from when we talked about how the solar system forms, but we can see what we call these stellar nebulas, these collections of gas clouds that form really several stars. So you'll have massive gas clouds that collapse, and when they have dense enough parts, that will collapse into really like a litter of stars. So here we can see what we'd see in the night sky, and we can see a gas cloud here, sort of a nebula. And newborn stars produce white patches in the cloud where starlight illuminates surrounding gas, so we can see this sort of cloud-like structure. And the cloud looks dark where dust particles block light from more distant stars, right? So we can see the cloud, but if it's more distant, dust will filter that light out. So this is, now a picture like this takes a lot of image processing. These are true pictures, and again, you have to understand when I say processing, it's not fake. A lot of students sort of say like, oh, it's processed, it can't be real. You have to remember your eyes only collect a certain amount of light. What we do is we collect large amounts of light for a long time, and because of that, we can see much sharper images and real colors that aren't visible to our eyes because our eyes don't collect enough light to sort of see things as they are. What's the true reality is that our eyes are very limited sensors. And so we build telescopes to see at light levels what we can't see. All right? But if our eyes were made like telescopes, we would see something like this. If your eye was designed to just view an image that's processed like this one, this is what you'd see. All right? Now, it might not be useful for surviving. Your head would probably be big with giant eye cups, but if you could imagine your eyes being the size of large beach balls, you might be able to see something like this, which would be pretty cool for stargazing, but not so good for, surviving on Earth. So let's just go. So now, when we look here, we sort of have a zoom in of these star clouds. We call this gas the interstellar medium, all right? And this is the dusty gas clouds of interstellar space. All right, so you'll often hear that term a lot, and the interstellar medium will be where the gas lives. That's okay about your internet connection. Everyone's going to have troubles at some point. But this gas cloud, right? This is what this sort of facilitates the gases that create these nebulas that condense and then become stars. So let's take a look at some properties of a mass forming cloud. All right. So gravity versus pressure. So gravity, we've talked about. Pressure, well, we're going to need some ideas there about pressure. So gravity can create stars only if it can overcome the force of thermal pressure in a cloud. So gravity within a contracting gas cloud becomes stronger as the gas becomes denser. All right, so if the gravity is stronger than the thermal pressure wanting to push it out, you can collapse. And that's a classic pressure. We can sort of understand the pressure of a gas, right? If you can't, just imagine a car engine or something like that, where you have gas expanding a piston or moving something along along the lines, or if you've ever filled a tire up with air, that's compressed gas. You can sort of understand thermal pressure there. But pressure is going to get more complicated, and we're going to have to talk about quantum pressure due to quantum mechanics, before our day is done, almost assuredly. So now let's look at let's get some insight into our star-forming cloud. So a typical molecular cloud, you'll notice that it starts off fairly cold at about 30 Kelvin and fairly sparse, 300 particles per cubic centimeter. To give you an idea, the temperature of Earth, for instance, the planet you're on, is about 300 Kelvin. And I always like to look this up, but I never memorize it. Hold on. Particle density of air. So if we look at air, the density of air. Oh, someone had a question? I didn't read them yet. I didn't go through them. So sorry about that. I'll look at them during break. So the N here, this is 300 particles in these dust clouds per cubic centimeter. The air you're breathing, so for air, right, N equals about 10 to the 19th particles per cubic centimeter. All right, and the temperature is 3 times 10, or not 3 times 10 to the 2, right, or 300 degrees Kelvin. All right, so you can see that there's a lot more particles in air even than in these gas clouds. So if these gas clouds are forming multiple star systems, they are huge. All right. So the cloud can prevent a pressure buildup by converting thermal energy into infrared and radio photons that can escape the cloud. All right, so radio waves pass through dust very easily, whereas visible light scatters off the dust. Okay, so let's go on. So you can see that this simulation here will begin with a turbulent cloud containing 50 solar masses of gas. So you can imagine this thing is light years in size. All right. Now, the random motions of different sections of the cloud cause it to become lumpy. So that nice shape we had in the last slide very quickly leads to some larger density areas and a lot of lower density areas, but it destroys that symmetry very quickly. All right. Now, each lump in the cloud in which gravity can overcome pressure can become a star. And a large cloud can make a whole cluster of stars. So like puppies, stars are born in litters. Okay? And we can see here, this is one of the iconic pictures of the Hubble Space Telescope. And these are often called the pillar of creation because these are stellar formula. These are stellar nurseries. There's stars forming inside here. Now you're looking at this in visible light. So of course, because there's so much gas and dust, you can't actually see the starlight forming through here. The only hint we have in visible light is these white edges of the gas clouds, all right, where the dust ends. Now, The pillars of creation are part of a larger nebula called the Eagle Nebula. I guess I don't know if you can see the eagle. I'm not very good at this abstraction stuff, but apparently there's an eagle in here somewhere. I don't know. Anyhow, if we look at it in terms of infrared, all right, we can start to see the little stars forming in these regions, in these pockets. We can see there's several stars forming in the what we call the pillars of creation, all right? And you can also illuminate, you'll also notice the background stars, which were fairly visible here. You can start to see the gas the gas structure is a lot more complex, okay? So this is what we can see by looking in that infrared region. All right. So questions? We're doing okay so far with this part? Okay, good. All right, so let's go forward. We'll get through that. So now we get to the stuff we've sort of seen before. Once you look in those lumps to individual star formation, you have these dense gas clouds, which, as we saw previously, form these disks. And we can talk about, I'll remind you that the particle motion is still random here, but you have conservation of energy and conservation of angular momentum lead you to go from sort of this everywhere disk to this sort of gas cloud to this ordered disk. All right? And then with collision, the disks start spinning faster, and it flattens out because the up and down motion cancels, and the round and round motion is additive. All right. So when we look there, we can start to see these things, and this is all just a review of the other thing we talked about, flattening. I kind of just go through this quickly to get to the point, because we shrink to the point where some things we didn't talk about because they were only we didn't see them, but as the disk is collapsing, we can see in the late stages of collapse before the star ignites fusion, the central the central star is not a star yet, so it's called a protostar, and we can see that it may fire jets of high speed gas along its rotation axis. All right, so this is things that we see rapidly rotating objects do throughout the universe, and protostars are just sort of the first look at this. Now remember, this probably happens because at this stage of the stellar life cycle, there's a ton of gas here, right? So that gas, as it heats up, may start to interact with the magnetic fields of the protostar and get shot out. Now, why don't we see our own star shoot out these jets of gas now? Well, because once the star is in the main sequence and the protostar becomes a star, the solar wind will push all this gas out. All right, so the gas that's there to be shot out in jets, there just won't be there anymore. All right, and jets can be observed coming from the centers of disks around protostars, and eventually all these jets from all the stars that have been born mixes into this interstellar medium. All right, and when we look at the galaxy, we'll get a bigger picture of what happens to this interstellar medium and the gases of the galaxy that actually, determine the life cycles of galaxies instead of just individual stars. There's another photograph of a flow jet, which we can see here. All right, so you can see here's the disk, and here's the flow jet. Now, what I want you to notice about some of the stuff we're looking at is these come from observations we can see, right? So we can see this stuff through telescopes, and then we apply the physics we've developed to create the simplest explanation. And that's what we're doing here. That's all we're doing. And to remind you, that's all that stuff we learned about. We learned a little bit about quantum physics. We learned about energy and momentum conservation and Newton's laws of motion. And using those things where appropriate, those models, or that framework, helps us describe what we see here. So that would be the same. So the meteoroid is and we just blazed over it. So the asteroid, right? As soon as an asteroid hits the Earth or an object from space falls on Earth, it is a meteorite. So the asteroid that came and likely killed the dinosaurs, once it hit Earth, it would be a meteorite, right? And then, but the interesting thing about that asteroid and the dinosaurs is there's good evidence for the asteroid killing the dinosaurs. However, there are competing theories. Most mass extinctions are linked to what we call TRAPS events, which is when like volcanoes the size of something like say Texas or bigger are active for tens, if not hundreds of thousands of years. And while the asteroid didn't help, there was a TRAPS event going on that's pretty conclusive. So it may be just a coincidence. There's a scientist who argues that. I always like to point that up. But the asteroid has a few bits of evidence that are pretty compelling. Namely, you can find rare elements. I think it's iridium that was expelled from the asteroid, and it takes a thin line that you can see in every record on Earth, every geological record, and there are no dinosaur fossils above that line. They all occur below it. So that's a pretty compelling piece of evidence. But then again, you know, that's the fun of science, is we're always trying to get a better picture of what happened. So it's my little thing on the dinosaurs. So let's take a look at some protostar facts. So of course the protostar contracts and heats until fusion starts. Then you're in the main sequence, right? Once that hydrogen fusion starts, you are no longer a protostar. You can think of it like with people, right? The protostar is when you're in the womb, right? As soon as you come out and you cut that umbilical cord, you are a main sequence human. And so that's the same thing with stars, right? They're sort of in this developmental state, and then as soon as they can heat up to undergo hydrogen fusion, they are born. So contraction ends when energy released by hydrogen fusion balances the energy radiated from the surface, right? And that is when the star sort of stabilizes. So it takes about 30 million years for a star like the Sun to become a main sequence star. Less time for more massive stars, okay? So some good protostar facts. And again, for star birth, we sort of saw the summary of those gas clouds. I'll sort of let you look at it and assume you can read it when we go through. So when we talk about massive stars, so on the high end, we've talked about high mass stars, but on the low end, there's a lot of almost ran stars, right? And you might be wondering, well, how big do you have to be like the smallest star? And we sort of saw, interestingly, that the smallest stars can be smaller in size than the biggest planets, but they were almost always more massive than the biggest planets. All right, and we can see these objects called brown dwarfs, which just don't start the process. All right, so a cluster of many stars can form out of a single cloud, and we're back to our good picture. Now, very massive stars are rare, and low mass stars are more common. So I want to show you that in a collection of 261 stars, right, only one of them will be supermassive. But I want to point out where our sun lays. So our star is about halfway between here and here. So our sun is small, right? Because you have your massive stars all out here. We don't fit into the massive star category. But I want you to take stock of something, that if you look at these 200, the total number of stars is 261. And our sun is bigger than about 225 of them. So our star, if we were ranking from largest to smallest, right, with 1 being the largest and 261 being the smallest, the sun would come in at about 11 plus 25. Our star would rank about 35th or 36th. That's pretty high on the ranking list, right? So I like to look at it, I like to present it this way when I'm talking about our sun, like it's people. So our star is like a person that is 6 feet tall. Someone who is 6 feet tall is taller than most other people. That's an objective fact. But you wouldn't describe someone as 6 feet tall as, it's not commentatively tall, right? It's not like an NBA player, NBA player. You know, like if you look at the NBA, Shaquille O'Neal is a large person. Like he is, everyone, even someone who's 6 foot tall will go, that is a huge person. I hope you all know who Shaquille O'Neal is. I hope that that isn't a too long ago reference. But if you and some of the very tallest, basketball players are 7'1", 7'2". Those are extremely tall. When you run across someone who's you probably run across someone who's 6 feet tall every day. You will take note of when you Yao Ming is a you will take note when you see someone who's 7 feet tall. It will, and you may go your whole life without seeing someone who's 7 feet tall in person, but you know they exist. So so that's sort of the way to understand sort of where our sun is in relation. It doesn't make sense to call our sun a small star because ranking wise numerically it does pretty well, but it's certainly not not among the biggest of the big stars, and the biggest of the big stars are far bigger than our own star. Okay. All right. So let's look here. All right. Any questions on that? We're good? Okay. I think we'll just move on. So we've talked about how the largest stars are, but there is a physical limit, and what I mean by that is a mechanism that prevents stars from exceeding an overall largest mass. All right? So photons exert a slight amount of pressure when they strike matter, and very massive stars are so luminous that the collective pressure of photons drives their matter into space. So let's talk about this one. What are we really saying here? We're saying that light can move things, but you might be wondering, well, I have a window right here. Light is shining through. Why isn't that light moving me forward? Well, actually, if we sucked out all the air and put me on an ice rink, the sun's light would actually start pushing me. All right, and you can actually look at a light windmill on the internet. I'll let you do that on your own. They sell them when you look at light windmill, you'll see it on the internet. They're usually you'll say, oh, I've seen that before. It's usually in a bulb, like so, and it has it has 2 diamonds. Right? And one's usually very reflective and one's usually very absorptive, right? And so usually this is the vacuum, this is a very low friction pulley it's on. They do have many examples on YouTube, and I'm sort of telling you to do them, but I don't know if you've noticed in this class, but I can't share YouTube videos very well. The software doesn't like it very much. So I've kind of tried and I've kind of given up on it. But yeah, YouTube, you can see a bunch of them. And but I'm just showing you what it is here so you know when you found the right thing on YouTube if you're watching this now or later. Okay? And so you'll see that the air is evacuated from this tube, and that if you shine light on the reflective part, you will push and drive the windmill to spin around. Okay? And so that's you can see right for yourself there that photons exert pressure when they strike matter. Now, if you're in a vacuum, right, and you have a ton of a very luminous star that's very massive, basically, once you reach a limit, there's a limit where you have too much output that you can't, you're losing mass, right? The photons will just start ripping up whatever there is apart. The pressure will be too great, and so that puts a bit of a hard upper limit on stellar mass. So observations have not found stars of more than about 300 solar masses, and these models suggest that radiation pressure will limit how massive a star can be without blowing itself apart. Now, of course, this is interesting because we're always looking for bigger stars that help us refine our theories and models to understand how that could happen, right? So this is one of those things where we're still looking at ancient, more stars to figure out what's going on. One of the interesting things that I want to talk about is the James Webb Telescope we're hopeful will illuminate the first generation of stars, right? These sort of supermassive stars that wouldn't have lasted very long, right? It's expected that there were these very massive. There's some special name from like population 3 or 1 or something, and that they're supposed to be very heavy, very short-lived, and exist in a universe that is different than the one that we live in today. Just a much younger universe. So that ought to be an interesting those will be interesting discoveries and interesting to learn about. We may be able to find that some of the very earliest stars exceeded this mass count, but they might have existed in a universe that was much hotter than our current one today. Or they almost certainly existed. Let me rephrase that. They existed in a universe that was much hotter than the one today. And what I mean by that is, today, the temperature of the universe is about 2.7 Kelvin. That's the background temperature. There could be a point where the background temperature, and there almost certainly is, where that background temperature is 27 Kelvin, right, during star formation, or maybe even up to 100 or so, where the background of the universe, right, just the universe itself, is hotter than that 30 Kelvin temperature of the gas clouds that start to condense. So that would almost certainly be a very interesting regime to study. That's certainly different than the universe we look at and observe today. So continuing on. We have all right, so that's our upper limit, and we sort of alluded to brown dwarfs when talking about this lower limit on a star's mass. All right, so if we look here, if we don't get to that 10 to the 7th Kelvin, fusion will not begin in a contracting cloud, and so basically, if I thought I was going to be creative here, but if something can stop the temperature from rising above 10 to the 7th Kelvin, fusion won't begin. All right. So thermal pressure itself actually can't stop contraction because the star is constantly losing thermal energy from its surface through radiation. So now what we have to learn about is the quantum pressure, all right, or electron degeneracy pressure that can stop a star from contracting. Okay. So what we want to talk about now is degeneracy pressure. All right. So now we have to. This is our first exploration into expanding our understanding of modern physics. Our real first expansion was talking about photon energy, and then we continued talking about nuclear processes. Nuclear processes are extensions of quantum physics and special relativity. But the laws of quantum mechanics, okay, prohibit electrons from occupying the same energy state. So let's take a look at what that means. So if we have energy states here, and our electron has a lot of properties, spin, just don't worry about the specifics here. So one energy in an electron can be uniquely defined as up or down in each energy level. All right, and you can only have you can only have one up electron and one down electron in each energy level. All right, and those are distinguishable, the spin up and spin down. But you can't have, for instance, if you look here, an energy level can only, you can't have something like this. That's not allowed. You have to have another space if you want to have up, up. So the correct way to do up, up, this is no. So you'll notice you have to have 2 slots in an energy to have 2 energy levels. This is okay. All right? Don't worry if you're looking at this going, what is he talking about? It basically, when we look energetically, what quantum physics does is it allows us to look at how electrons can energetically arrange themselves, right? And so we have these diagrams, right? If an atom absorbs light, the electron gets promoted, can go to different energies. You remember that? So it goes up the ladder. And then if the electron loses energy, it goes down the ladder. But you can only have, it's sort of like a chair in musical chairs, you can only have, each level has room for 1 down chair and 1 up chair. All right? And you can't put 2 of the same kind in a chair. It's a lot like musical chairs. So how we're going to understand degeneracy pressure, because it's a little abstract with electrons, is we're going to do a version of it with people. All right? So people, you'll notice that you can think of the people as the electron, and the chair is where it can sit with the energy. All right? So if you go into a big auditorium, imagine we took our class and went to Citi Field, right? There would be a bunch of ways we could be arranged. We'd have the whole run of the place, all 12 of us, or all 13 of us, right? We'd have the whole run of the place, and you could arrange us in a whole bunch of ways. But now imagine we went back to the classroom, right? Well, there's not as many ways to arrange us, but there's a lot. Each student can sit in different chairs. But now if we take away a lot of those chairs, you'll notice that it becomes very tight, right? And there's no lap sitting in this version of musical chairs. You can only have 1 person per 1 chair, and you'll notice that the number of arrangements, the ways the electrons can arrange themselves, decreases as you take away the chairs. And so that's degeneracy pressure. All right? It says, unfortunately, this is only half true. It says particles can't be in the same place at the same time, or can't be in the same state in the same place. This is half true. So if we want to be a little more accurate here, we want to cross off particles, and we want to say fermions. Fermions can't be in the same place at the same state in the same place. Bosons can be. We don't want to talk about bosons, but we want to be accurate. And this doesn't depend on heat content. This is an internal quantum property. All right? And it's because of degeneracy pressure that we know black holes exist. And I want to talk about that. We're going to talk about that in greater detail, but you can see here, I want to draw something for you. So this, what I'm writing down here is a little equation. Don't worry about it. All right? This is called the Heisenberg uncertainty principle. All right? So basically what it means is that you can have a minimum uncertainty. All right? So if you know your position more precisely, you know your momentum less precisely. And let me show you sort of how this works. So we're going to do this with concentric rectangles. All right, so that's rectangle 1. Now imagine I'm a particle, and that's just the point of the hand. It's free to move everywhere. Okay, so right now it can cross the box, and its momentum can be pretty well seen at different parts throughout the box, right? It has to travel to other parts of it. But its position is not, it could be anywhere in this box, so it's not super well known. You might be saying none of that makes sense. It'll make sense as soon as we draw a second box. Now in the second box, I've decreased my uncertainty in X, right? Now instead of being able to be anywhere in this box, I'm confined here. But you'll notice I hit the sides much more quickly. So it's a lot harder to look at my uncertainty and momentum, and that increases, all right? And so basically, you can make the square ever so smaller, right? And you can make it smaller. You can go to delta x is so low such that, I'll change colors here, that p, that this implies that the velocity is equal to the speed of light. And that brings us to another barrier in special relativity, in relativity theory. All right, and this relativity theory says that this quantum degeneracy pressure can only shrink something down. We can only have so many chairs such that the momentum for the particle doesn't work with people really, but the particle's momentum is limited to being the speed of light. Any smaller, and you break the laws of physics and you can't exist. And this is going to be the primary argument when we get there behind the insistence on the existence of black holes. All right, and we're going to see how this applies. We want to introduce this, and we want to keep it in mind as we go forward. This concept of degeneracy pressure is going to help us with the mechanisms of understanding the creation of black holes. So we want to, and neutron stars, to be fair as well. Well, it helps us understand the creation of white dwarfs. But dead stars, the bizarre things that happen to stars when they die, is based on degeneracy pressure. So we want to sort of not forget this. Okay? So questions on degeneracy pressure or clarifications? This is a kind of a weird concept, and I'd understand if there are questions on it. Well, I understand if there's questions on anything in the course, to be honest with you, but I expect there to be a few here. Okay, well, I'll give you a minute, but if you have them, you know, don't be afraid to ask them later as we go on. As long as I hear the text box blink, I can address your question. All right. Okie dokie. Hold on. All right. Okay, so don't be afraid to ask as we go on, but we now want to talk with a little bit more detail about brown dwarfs, which is our first run-in with the degeneracy pressure. All right. So basically, when we talk about if you don't have enough mass, right? So degeneracy pressure will halt contractions of objects that don't have a mass that exceeds 8% of the sun's before the core temperature becomes hot enough for fusion. So basically, you can look at it as sort of like this. So let's do some ellipses. Let's do concentric. Hold on. All right. Okay. So basically, we have a race going here, right? Where'd you go? Okay. So if we look here, we have, as we go slower, we always have degeneracy pressure, so we'll call that degeneracy pressure. That's always going up, right? Because your number, you get smaller and you increase that pressure as you go down. Now, basically, if you how much freedom you have, how many chairs you have, will determine how hot you can get before you run out. All right. So basically, what happens in a brown dwarf is that there's not enough mass, and you run out of chairs, and all the electrons are set. And if the electrons are set, if they're in their chairs, if they're in their energy levels, there's nowhere for the star to go. So with less than 8% mass, as you go down here, right, you heat up, you get hotter, and then all of a sudden, you can't shrink anymore. All right? But because you filled up all the chairs, and you're not massive enough, and you didn't get hot enough to start fusion. So you're just sort of stuck. And this is a brown dwarf. All right? So these are star-like objects that are not massive enough to start fusion. They get pretty warm, but they get hotter than a planet would say, but you have to get an internal temperature of more than 10 million degrees in order to start that fusion, really more than 14 million degrees. And that's when fusion will start in the core. So if you have enough mass, say, look at this and look at it as more mass, now you have more chairs available to you, and you can keep shrinking and get hotter and hotter and hotter, and then you can start your fusion before you lose all your chairs or you increase your degeneracy pressure too much. Okay? So that's essentially what a brown dwarf is. You need to have enough mass so that you don't run out of places to collapse to, essentially. And a brown dwarf will emit infrared light because of the heat left over from its contraction, and its luminosity will gradually decline with time as it loses all thermal energy. All right, so basically, once you collapse, if we make a little graph here, all right, we'll call this temperature. We'll call this time. All right. And so what happens is as you collapse, right, your temperature goes up, 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 and up, but you just don't have enough mass to start fusion. So you plateau, and then if you can't do this, right, you radiate energy away very gradually through infrared and other things. I'm being a little dramatic here because I can't possibly do it slow enough. But you start to lose temperature, all right, because your thermal energy gets lost. And that just makes it easier to stay energetically bound, right? As you lose energy and cool down, you're not gaining more energy states, or anything like that. So brown dwarfs eventually cool off, and they're much harder to see because we need infrared, and we can see that there's many brown dwarfs, but these are just the recently formed brown dwarfs, right? Because if a brown dwarf is too old, it'll be too dim to see, all right? Or at least see with light. They should be visible gravitationally. That's another story. All right. So stars more massive than about 300 solar masses, these would blow themselves apart according to our models and our understanding of quantum physics. And stars less massive than 8.08 solar masses, or 8% of the sun, can't sustain fusion. So I want you to note that our explanations, our whys here, are based on actually, you know what? I will write it in a text box. So we can see here that stellar Ys, like why can it only have a maximum of 300 solar masses? Why is there a minimum on star formation? Why doesn't it keep collapsing forever and ever? So stellar Ys are based in quantum mechanics. All right? And we see that at both ends. At the high end, we have radiation pressure. Nope, hold on, bad. At the high end, we have radiation pressure, right? Here. I don't need an arrow there. And at the low end, we have degeneracy pressure. Both of these are described by quantum physics. All right, so quantum physics is important for us understanding the mechanisms of stars and what limits them from shrinking indefinitely or blowing up. And in fact, black holes themselves, you might say, well, wait a minute, doesn't a black hole keep shrinking and shrinking? Well, black holes represent a regime where we don't have physics to describe them. We can only describe a black hole to its event horizon. What goes on inside a black hole, we don't have physics for. So in that sense, our physics can help us understand what we see. In a black hole, we certainly can't see what's going on. But to bring it back to what I was talking about with stars, we're going to see that that to do cosmology and understand these objects, we actually need to know quantum physics and general relativity. But general relativity, you'll often hear that these theories don't play well together, and they don't. General relativity is a continuous theory, which means the universe is continuous, and quantum physics assumes a discrete universe. So they are fundamentally different, but elements of both will be used. They sort of find intersections here in astrophysics, and that's pretty cool. So let's move on. All right, and now what we want to do is, now that we've sort of seen, we've talked about stars being born and the range of stars that can exist, we want to talk about what life is like as a low mass star. We want to see all the life stages. All right, so we'll want to see how they live, but more importantly, and perhaps more excitingly, how do low mass stars die? All right, so let's take a look. So they sort of give it away here, and we sort of covered steps 1 and 2 of this stage. And we need to expand on 3, and you'll notice that we expand, but then you'll notice we become stable again. This is called a helium-burning star. Then we become a bigger giant, and then you'll notice there's this pretty spectacular explosion, and then this little white dwarf is all that's left. All right? So again, we've focused on here, but we're going to look a little into the other stages of the life of a star. All right. Now, the star remains on the main sequence, as we've said before, as long as it can fuse hydrogen into helium in its core. But it's important to note, right, that if this stops, if this becomes all helium, all right, that doesn't mean fusion stops in the star. It just means that now it's so hot outside that you have a shell that starts to form. So there's still fusion going on in the star, but it's no longer contained to just the core. All right, it's an outer layer fusion. And as you can see, you can start to understand some of the dynamics. This outer layer fusion, you still have this. You have this inert core getting smaller and smaller, not radiating. You have a lot of this fusion expanding the outside of the star, making it bigger, right? But you have this core as inert, and so it shrinks and shrinks and shrinks. So is it that the star dies completely or just starts over the process of life from baby stage? That is a deep question with the real involved answer is today, tomorrow, and the week after of the course, and maybe the week after that. But basically, stars do die and leave behind a corpse. But the short answer is that what they expel can contribute to the formation of new stars. All right, so we'll see that in a lot more detail as we go on. But right now, we just want to understand the expansion of all this business going on here. And so you can see that if you have shell fusion going on, this will allow the boundaries of the star to be pushed out, but the inert core will be getting hotter and hotter, and our solar thermostat is broken. Okay? And we'll see some pictures that illustrate this point. Okay. So observations of star clusters show that a star becomes larger, redder, and more luminous after its time on the main sequence. So we want to go here. So we'll notice the sun will become a subgiant, it'll stabilize, and then become a red giant. And there will become a point where the core of a star is hot enough for helium fusion. That will be interesting. That's that second stable-looking phase. So if we look here, oh good, I'm glad that this isn't a simulation. We can look at it here with the broken thermostat. So here in the main sequence, you'll notice they do it a lot nicer. We have our core, our radiation layer, our convection layer, and our photosphere, right? Our sort of atmosphere with all that other stuff. Now here, we have an inert core, right? A contracting inert core. So this is getting smaller, but because it gets smaller, it gets hotter, and it builds up a shell of hydrogen fusion. All right. So that shell of hydrogen fusion will not be regulated by the contracting because you're not fusing in the core. You just have nothing going on. It's getting hotter, but there's no fusion going on in the core. So you just have this expanding shell layer, which is blowing out the photosphere and making the star bigger in size. All right. And that's because you break that thermal equilibrium. If you remember, we talked about how gravity and fusion keep each other in equilibrium. That equilibrium is broken, and the star starts to do funny things. Now, you have to get up to a much higher temperature before you start fusing helium into carbon. All right, but you can. It requires a much higher temperature. We're talking nearly, I don't remember offhand, but I think it's north of 100 million degrees Kelvin. So much, much higher than hydrogen fusion. And you don't get as much energy out either. That's the other thing, is when you become a helium fusion, you get a carbon nucleus, but it is not more energy. The most energetic fusion reaction is hydrogen to helium. So the fusion of the two helium nuclei doesn't work, so that's why we need to combine 3 of them to get carbon. What it means by works and doesn't work is there are rules for nuclear combination. They are complex and well beyond the scope of the course for really getting into it. But you can just take my word for it there, I suppose. If you really want to get into it, you can. They might not be too hard to follow, but you'd be able to look at them qualitatively. What can combine, why it can combine and can't combine. So you might basically what probably happens is if you were to try to do this, you'd get 4 protons, which would get you to, on the helium, let's see, so you have lithium, atomic number 4, beryllium, right? So you might be wondering, well, wait a minute, you could get beryllium, but you have to remember when you fuse these, you also are getting these neutrons. Now, I don't think there's a well, so no, if you had 2 and 4, it might be that you need to get some extra energy for the beryllium atom. I'm not sure why it doesn't form a stable, because you'd have exactly as many neutrons as you would protons. But I must take off my cape and reveal I'm not a nuclear physicist. So these rules, I know you can look them up and get reasons why behind them, but I'm not an expert in them. But anyway, I'm going to take their word that it doesn't work. I don't see why it doesn't, but anyway, you can combine 2 of them to get 1 carbon. All right. And so in a low mass star, when the core temperature rises enough for helium fusion to begin, I thought that's a question. So basically what happens is after you get that core fusion up and you have the helium and it gets hot enough for helium to start fusing, right before that, the thermostat is broken in a low mass red giant because the degeneracy pressure is supporting the core. Now the core temperature rises rapidly when helium fusion begins, and the helium fusion rate skyrockets until thermal pressure takes over and expands the core again. So basically that helium flash will cause an explosion, right? You'll have this helium core fusion, and this hydrogen shell fusion, this will create a core, a flash, and give you a stable helium-burning star. But this does not last long. All right? So models show that the red giant will shrink and become less luminous after helium fusion begins in the core. You'll get a flash. You'll shrink like this, but now you'll get to a inert carbon core, and that will start a helium shell layer and a hydrogen shell layer, and you'll become a red giant, a supergiant, okay? And so you'll become much bigger, and the degeneracy pressure, much like with the brown dwarf, when you run out of mass, there's just not enough mass in low burning stars to raise the temperature so high that carbon will fuse. All right, so you run out of temperature and you stay this inert carbon core, and then that's when it gets really exciting. So when that happens, you build up and then you explode away in this gigantic explosion called a planetary nebula. Now, this is a name that's not descriptive. It's a name that sticks around. There's nothing planetary about it. But basically, it was thought to come from planets, and they don't. These are the explosions of low-mass stars. Now, high-mass stars will undergo a process called a supernova. A supernova is different than a planetary nebula explosion. So they ought to just call it, and they don't call it a nova for very specific reasons too. That might be a more appropriate name for it as a nova, but you could call it something else. But planetary nebula is sort of the historical name that stuck, and essentially this is what happens when a low-mass carbon core star explodes and leaves behind a white dwarf. All right, and they're pretty spectacular images. So we can get some details behind this double core fusion. Well, we already talked about this. Yeah, we already talked about that, really. I'll just leave it on there if you want to read it. All right. So the double shell fusion ends with a pulse that ejects the hydrogen helium into space as, again, a planetary nebula, but you could call it a low-mass star explosion. I'd be happy with that. But on a quiz, you'll need to know what a planetary nebula is. The core left behind becomes a white dwarf. We already covered all that. It's redundant. But you'll notice that some of the pictures are pretty spectacular. Like you have this planetary nebula with these lobes. Keep in mind that these are stars exploding, so the Earth would be a small, tiny bit somewhere near the center of this explosion. It would be a bad day to stand on a planet when a star goes nebula. You would not want to really deal with that. Okay, so we've already talked about this, but yeah, we talked about this. So you can just see it sort of in the slide if you want to see it written down or slower. This is just saying what I said earlier in a different way about the core being inert and fusion not being able to progress because you just don't have enough mass, right? The degeneracy pressure says, nope, we're done. And if there's no place else to go, the core can't contract. And if it can't contract, it can't raise its temperature. And if it can't raise its temperature, it can't make carbon fuse. Okay, let's see where we are now. Can't see that one. So we'll do this before. Give me 1 second. I just want to see when we're into the next section. I honestly thought we were going to get there by now. Yeah, okay, good. So this is our last slide here, and then we'll go on break. So to sort of summarize and recap is if you look at our sun starts on the main sequence, right? And in the main sequence, we have inert helium, but hydrogen fusion in the core, all right? So wait a minute, this is an inert helium core? Never mind. We have our sun where we're rapidly fusing hydrogen into helium. Then we start to have a lot of helium in the core, and we expand, our thermostat gets broken, and we become a subgiant, right? So the subgiant has an inert helium core, and then it has a hydrogen shell, which is what makes it bigger. And that goes on for a while, and the core temperature raises, and then you have this helium flash, and now Here you have helium fusion, and the helium fuses to carbon. And then after that happens, you turn your core into carbon. That will stop, and you'll have an inert carbon core, and you'll get a helium and hydrogen layer, and that will build up until you get spikes of flashes, and you have the carbon core remains inert as a white dwarf, and you have the rest of the star explode away in a planetary nebula. So all that gas goes back into the interstellar medium, and your carbon core becomes a white dwarf. Okay? And the white dwarf cools over time. All right? So that should be good on part 1 of today's 2-part doubleheader. So I'm going to stop recording now so this video can process.